Hello everyone. This is Team E.T.A's physics project on multiple particle systems. And to begin with, we are going to be discussing magnetic dipole-dipole interaction systems, which include the various types of magnetic materials that exist, nuclear magnetic resonance. We will also be discussing quantum entanglement and how it ties in with quantum computing. To begin, we have to define what a magnetic dipole-dipole moment interaction is. And in the most basic of terms, it is any two system that has at least two particles with their own magnetic moment that are close enough to each other as to generate either a force or a potential energy. This is most commonly introduced to us physics majors as dipole-dipole interaction forces, which refers to any time when two elements bond together, which naturally creates ununiform distributions of positive and negative charges, which then generate a magnetic moment that can interact with other bonded molecules to create force interaction forces. There are many different ways to represent magnetic dipole-dipole moment interactions with math. This is one such way. This is a equation that tells you the potential energy generated by this interaction. And the only assumption you have to make is that the two particles must be far enough apart as you can treat them as point dipoles, which is just a fancy way of saying you don't need to worry about nonlinear effects and or weird geometry. Interestingly, this function has a delta function that vanishes everywhere except for the origin, as to not invalidate Maxwell's equation that the magnetic field must be zero everywhere. This equation does not include that for unknown reasons. I tried searching it up, couldn't find it, but it does tell you the same information. And in this expression, we have more physics 425E friendly terms, which is saying that it has like spin in the gyromagnetic ratios, which is stuff we've seen in class. And as this equation and the previous equation both utilize the dot product heavily, which makes sense as this potential energy is largely governed by how far away the two particles are from each other, either along the vertical and or horizontal axis. Moving away from math and more to the fun physics side of it, we can discuss how dipole-dipole moment interactions generate magnetic materials. There are three main categories for magnetic materials: a ferromagnetic, a paramagnetic, and a diamagnetic. A ferromagnetic is what we usually in the everyday sense call a magnet, which are permanent magnets where the dipoles of each individual particle within the magnetic material align with each other as to create a giant magnetic moment, which is so large that the material itself can generate its own magnetic field. A paramagnetic and a diamagnetic material both have to rely on an external applied magnetic force to have magnetic properties. In both materials, the magnetic moments are originally completely random and only align either parallel or anti-parallel once a magnetic field has been induced onto it. In a paramagnetic material, the magnetic field creates a positive magnetic force, which you can see here, where this bar magnet is being applied to this aluminum, which by itself is not naturally magnetic, but once it has a magnetic field over it, has a attractive force, magnetic force. A diamagnetic material is the opposite, where it has a natural repulsive force. You can see this here with this frog. Many large-scale organic materials are naturally diamagnetic. And in this example, this frog is wanting to be pushed away. So a repulsive magnetic force that just so happens to even out with the gravitational force as to allow it to levitate. As you can see right there, he looks kind of scared. So a more experimental application of dipole-dipole interactions include nuclear magnetic resonance spectroscopy, which utilizes some math that we have used in class thus far. But this technique is usually used to determine the structure of organic compounds. And the basic idea is that you have some kind of set of electrons in a magnetic field. And as you increase those magnetic fields, the eigen energy states will naturally widen. So it's going to be easier to identify whether it's a spin up or spin down electron. And as you can tell, the mathematics follow verbatim almost. the problem we did in class where we had an electron in a magnetic field, and if it was spin up, it went to the positive energy eigenstate versus negative energy eigenstate if it was spin down.
Thank you, Matt. So we're going to transition here from thinking about particles in relation to magnetic dipole-dipole interactions to the quantum interactions or quantum entanglement. Now, to start, similarly how we were introduced to quantum mechanics through the Stern-Gerlach experiment, we're going to be introduced to it here with something called the EPRB experiment. It's very similar to the EPR experiment, except there was a person named David Bohm who revised it, so we slapped the B on there. Now we start out initially with a box, and inside that box, there is a net zero spin particle. When it decays and goes in opposite directions with this matter and antimatter constituent, each of those have a spin. The electron has alpha, the positron has beta. Now, based on the conservation angular momentum, alpha plus beta should equal 0. Now, classically, this makes sense, and we can develop a relationship between the correlations, whether it be a positive correlation in which both of them are spin up, or a negative correlation in which they're both spin up and down. They might ask, how can they both be spin up? The way to do that is if you measure the electron one way and then measure the positron with an exactly pi shift the other way, they're both going to have spin up. Now, when we go to the next slide here, we can see a better representation of how the classical interpretation is made. When you're at pi over 2, in where theta is pi over 2, and theta is the difference between alpha and beta with an absolute value here, there's no correlation. It's all random. If it goes slightly up, it's up spin, slightly down, down spin. Now, when we go down to the next slide here, we can see there the classical interpretation, which is seen as a linear trend, and the quantum/experimental representation, as we can see, as a negative cosine of theta. Now, what's important here is the fact that it's not linear, that the experimental and quantum theory both agree with each other and disagree with the classical interpretation of it. And this idea that it's not linear can be broken down into a representation that relates alpha and beta to one another. Now, this is important because it treats now the measurements of alpha and beta related to each other. Normally, we'd treat them as independent systems, but somehow they are related. That's quantum entanglement. When you measure one particle, alpha, and you can directly see the measurement of the other one, beta, they're interconnected. They are directly dependent on one another. And this idea violates local realism. Locality, in this sense, is the idea that whatever causes a particle to move or any interactions between it must travel at the speed of light or slower. This interaction, this quantum entanglement, happens instantaneously, breaking that. The second idea is this realism, where the external universe behaves normally even when not measured. Like if I looked at the moon and then looked away, the moon should still be at the same spot, maybe moved a little bit. We know in quantum mechanics that when you measure something and naturally observe it in its eigenstate, those are two different things. Now, when we go to the next slide here, we'll leave it off to Morgan.
Thank you, Kyle. Thank you, Matt. So we talked so far about a lot of principles of quantum mechanics, but there are ways that we can actually have these applied in the real world. And so what better way to describe that than with quantum computing? To make it very short, quantum computing is a fantastic thing. It's essentially the computer for your computer, or like the personal calculator is to us. As we have bigger and larger problems that require bigger calculations to handle, eventually there are going to be some slip-ups, more errors, more unknowns that we have to account for. And that is precisely where the quantum computer comes into play. It's made up you might be asking yourself, well, what could we possibly need it for? That just sounds like a general bigger calculator or computer. Why do we even care? Our computers should be good enough. We've been using them for all our entire lives. And what does it even look like? Well, if we go to the next slide, we have a fantastic photo here of IBM at an event in late 2017 where they unveiled their 50-qubit quantum computer. And for a sense of scale, there's a gentleman who's presenting various cool bits of information. So what do we need for a quantum computer? I'm glad you asked. A quantum computer requires a few things, mainly things called qubits, superconductors, and a few of the principles that we've talked about before. Qubits are much like our binary bits that we use in our classical computers, where bits can be represented as either a 0 or a 1, like flipping a switch on and off, but qubits have the ability to have the principles of quantum mechanics applied to them, so it can be more than 0 or 1. There can be a superposition between those states. So with that being said, apologies. Superconductors can make great use of this. Superconductors are materials that at very low temperatures have the ability to let electrons and other such tiny particles move without any resistance, which becomes very important because we don't want the quantum states, the quantum entanglement of our qubits to be disrupted. And so the fewer chances of that happening are, the better. Next slide, please. I'll leave it off to Kyle to explain further.
Thank you, Morgan. So the quantum mechanical aspect of quantum computing, like Morgan stated, is that the idea that you can rewrite the eigenstate in terms of a superposition of the 0 and 1. Here, classically, we'd have a 0 and a 1 binary bit, but here we can treat those 0 and 1s as kets. Now, the idea here is how we can use our 0s and 1s is very similar to what we've done in class. We can manipulate those 0 and 1s eigenstates using different, they're called quantum logic gates. Now, what's the beauty is that you can rewrite the majority of logic gates that we've seen in class using this unitary matrix. And the idea of a unitary matrix is that when you multiply its complex conjugate with itself, you get the identity operator, and it's invertible. And when you multiply its invertible operator with itself, it also gets the identity operator. Now, here is the normal classical interpretation of logic gates. You have a set of inputs, 0 and 1s, and based on the different combinations, we get a single output, a 0 or a 1. Now, NOT is a special one because it only requires one input, but the majority of them require 2 inputs and spit out 1 output. Now, when we go to the next slide here, we can see the quantum interpretation of this. Now, the identity gate here can be rewritten as that unitary operator where we can manipulate our theta, our phi, and our lambda. And by playing with all of those, we can get the poly gates even to the poly matrices that we've seen earlier. Something to know also is that the P gate, if you go, there we go, with our P gate here, that is mainly used to do phase shifts if required to. And then the Clifford gate, which is something unique that I did not learn about until now, has to do with normalizing the qubit, which is really important when dealing with probabilities and such. Now, the complex vector space in which the qubits live will grow exponentially with each addition of qubit, where we have d being the dimensions of our complex system equaling 2 to the power of n, where n is the number of qubits. Morgan earlier stated that that IBM was using, or Google was using, a 15 qubit system. 2 to the power of 50 is 10 to the power of 15 systems involved. So even with 50 qubits, it gets pretty complicated quick. Now, because of this, whenever you go above 1 qubit, tensor products are involved to deal with any type of calculations. Now, I don't have any math background on tensor products, but what's important to note is that even with the picture to the right and the bottom, the AC, AD, BC, and BD, we can still represent those as eigenstates, where AC is the eigenstate in which both A and C would represent a 0, 0 eigenstate. Okay.
Thank you, Kyle. With that being said, let's touch up on a few final details. There are some challenges with quantum computing because, again, we're dealing with tiny little particles, qubits, quasi-particles, atoms, even photons can be used for qubits. Superconductors, as I mentioned before, need to remain cool, usually. IBM keeps theirs about 1/100th of a degree above 0, which is very cold. But a fun little fact is some superconductors don't have to be that very cold. There's actual interesting science that a sort of race, if you will, where people are trying to get warmer and warmer superconductors, some that are getting very close to room temperature. Um, Qubits, being the tiny particles that they are, can be disrupted with what is called outside noise. We call it their sensitive atomic things. So the tiniest bits of radiation, for instance, impact enough force that can disrupt that entanglement, which is so very precious to the whole point of quantum computing. So stuff like that can cause disruption. Some companies like Microsoft like to encase their qubits in protective equipment, protective chemicals to ensure that there's more longevity to their qubits. So the big question, how can quantum computing impact our lives? Many numerous ways, cybersecurity being the biggest among them. I mentioned earlier that the sensitivity of these qubits is pretty strong, and things like radiation of all things can impact their entanglement, which can be a good thing if you're trying to transmit sensitive information from one place to the other. If someone's trying to analyze your qubits, similar to the Stern-Gerlach experiment where they were analyzing the spins of the silver atom electrons, uh, it affects the state just enough to where it could disrupt the entanglement and destroy, collapse the whole information flow. That's a pretty great thing. On the downside, though, because quantum computing is so advanced compared to classical computer computing, our current methods of encryption are not going to be stable for very long. Because as you heard from Kyle, the 50 qubit computer from IBM is capable of an enormous amount of system and computations alone. And as the number of qubits increase, so too will the capabilities of the quantum computers. So modern encryption has to improve. Quantum computing is coming larger on the scene as we speak. Logistical challenges. I mentioned earlier of the idea of computating a very complicated problem. The more variables you add, the tougher it gets. It's like adding more parentheses and variables in your own calculator. Somewhere you're going to slip up and make some errors. Quantum computers, obviously, with their capabilities, can handle such challenges. Similarly, other big problems like financial and risk assessments, the simulation of molecules, transportation analysis, weather, climate analysis, and many more things can also be handled more smoothly with quantum computers. Oh, and here I will briefly describe is an image from IBM where in one of their products they were year by year they had a roadmap. They have present tense a roadmap of how many qubits they're working on their various products. In 2019, they had about 27 for their Falcon. The end of 2022, they had over 400, and they're estimating by the end of this year to have over 1,000. You remember Kyle saying that the computer from IBM with 50 qubits could do so much? Well, imagine what 1,000 qubits are capable of. Next slide, please. And you yourself can also play with some of the quantum computing code if you are tech savvy. Some of the companies I mentioned before have generously provided their source so that you can tinker away and get some hands-on experience. And that is all. Please like and comment and subscribe to our YouTube channel.